Welcome back and thank you for joining me. In this video, we'll explore how to determine the asymptotes of rational functions. Identifying asymptotes is very important because they provide the basic structure of the graph. Once the asymptotes are known, the rest of the graph is often much easier to complete. Now, rather than simply memorizing the steps used to find asymptotes, I would first like to explain how they are formed and why they exist. When we understand the reasoning behind a mathematical concept, we are more likely to remember it, apply it correctly, and use it to solve unfamiliar problems. We'll begin with the vertical asymptotes. Recall that a vertical line consists of infinitely many points that all have the same x-coordinate. For example, every point on the vertical line x equals 2 has an x-coordinate of 2, while the y-coordinate can take any real value. A vertical asymptote is also a vertical line, but how is it formed in a rational function? Well, recall that a rational function is formed by dividing two polynomial expressions. Polynomial functions are continuous for all real numbers. However, in a rational function, the denominator may contain a variable and the denominator may take a value of 0 at specific values of x. Since division by 0 is undefined, then any value of x that makes the denominator equal to 0 must be excluded from the domain. In grade 11, we refer to these values as restricted values. Now, what happens to the graph of a rational function at a restricted value? There are two possible situations. In this lesson, we'll examine both cases and explain them algebraically. Case number 1. Y equals 2x minus 6 over x minus 3. So first of all, what we want to do is factor numerator and denominator. So especially the denominator must always be in factored form. So in our case, then we're going to say that the factored form will be 2 times x minus 3 over x minus 3. Now, if you remember in grade 11, we said you have to state restrictions before simplifying any terms or any common factors. And the restrictions are found by looking at every factor and making it different than 0. So x minus 3, we're going to say, is the only binomial in the denominator, has to be different than 0, which means that the restricted value of x will be 0, x equals different than 3, so our 3. Now, as you can see in this case, we ended up with two common factors in numerator and denominator, so the simplified form of this function will be y equals 2. So what that means is that this function and this function in here should actually represent the same graph. However, they're not entirely the same. That is because this function had a restriction and this doesn't seem to have one. So to make sure that we acknowledge that, we have to write a comma and then add the restriction beside it. Now we're going to say that this function here and this one here are the same function, okay? So, or represent the same function. Now, what happens to the graph of the function in this case? Well, when it comes to graphing, then you can graph this function by simply graphing its simplified form. So let's do this together down here. So I'm going to just draw the axis first. So here is the y-axis, here is the x-axis, and we have the y value equal to 2, which means that the graph of the function will be a horizontal line that passes through y equals 2. X can be any real number, and as you can see, y doesn't depend on x at all, and that's why x can take any value. However, the function is not defined at x equals 3, so let's find x equals 3 in this case. And I'm going to go on the x-axis. And at x equals 3, the function is undefined. So what that means is that the function shouldn't exist at x equals 3. So we're going to get to x equals 3 and make a small little gap in there. That was a big gap. All right. And right here, we're going to say that the function will form a break or will form a hole. And that happens when the numerator and denominator will have a common factor that removes the restriction. Now, these are normally called removable restrictions. Okay, and we're going to talk a little bit about it, a little more about it later. Now, we're going to take a look at the next example. We have y equals x plus 1 over x minus 2. Now, there is nothing to factor in here. There are no common factors, so we're going to jump to restrictions. So we'll say that the restrictions are that the denominator cannot equal 0, or x minus 2 has to be different than 0, which tells us that x has to be different than 2. So now we're thinking if x is different than 2, then the graph of the function will never pass through x equals 2. I'm just going to write this down here. Graph can't pass or can't have any point with coordinate x equals 2. Now let's take a look at where all these points are. I'm going to draw the axis first, the x and the y axis. And here is x equals 2. And this point here has a value of x equals 2. So we're going to play a little bit around with this. This says x equals 2, x equals 2, x equals 2, x equals 2. At all these points, as you can see, at this point, x equals 2, and this one here in the negatives. Also, at these points in between, right? And at the points in between of the between, if you want to look at it this way, and maybe we should say at every single point in here. And if you were to actually count all these points where x equals 2, that will form a vertical line. Now, the vertical line that is formed at the restrictions is called the vertical asymptote of the function, because the function will never be able to cross this line, or as we call them, this asymptote. And now we're wondering, but what happens if the graph decides to approach the asymptote? So where would the points be located? Now, remember that rational functions are continuous curves, are represented by continuous curves that are interrupted by their vertical asymptotes, but they're still continuous curves. So the function doesn't behave randomly, so it's not going to have one point here and one point in here. There has to be some pattern. So in order to understand this, we are going to approach x equals 2 from the right-hand side of it. So x approaching 2 from the right-hand side, and then we'll approach x equals 2 from the left-hand side as well. But let's start with the right side. If x is approaching 2 from the right-hand side, it means that, say, x equals 2.000001, for example, then the function will become y equals 2.12345 zeros and a 1 plus 1, and then divided by 2.000001, and then minus 2. So very simple mathematical operations in here. If you have a number slightly more than 2, add 1, then you're going to get 3 and a little bit more. And if you subtracted 2.0001 minus 2, then you're going to get 0.000001. So a very small, close to 0 number, or as we call it, the 0 plus. Now remember, when we divide a constant by 0 plus, we get infinity. So therefore, we're going to say that when x is approaching 2 from the right-hand side, the y values are approaching infinity. So that means that the graph of the function is going to go up like this as it approaches the vertical asymptote. Now, vertical asymptotes are never crossed. They're restrictions. Once a restriction, always a restriction. Now, what happens when we approach 2 from the left-hand side? When we approach 2 from the left-hand side, it means that when x is approaching or is taking values of 1.99999. The values of y in the function will become 1.99999 plus 1 divided by 1.99999 minus 2. Now, as you can see, the numerator is going to be about 2 plus 1, about 3, but a little bit less than 3. Remember, 3 minus is a positive number, so it is like 2.99999, and another 9 here. And then 1.99999 minus 2 is going to have a difference of almost 0 because they're very close to each other, but it's going to be 0 on the left side or a 0 negative. So having a 3 minus divided by a 0 minus means that the answer is going to be negative infinity. So we'll say that when x is approaching 2 from the left-hand side, the y values will approach negative infinity. And that tells us that the graph of the function is going all the way down. And in conclusion, we're going to say that not every restriction in the domain will create a vertical asymptote. Why are we saying this? Remember that the restriction x different than 3 in here didn't make a vertical asymptote, it made a hole. But a restriction of 2 in here made a vertical asymptote. So how can we tell? Well, if a factor in the denominator is cancelled by a common factor from the numerator, it will create a hole. Okay? Now, if the factor in the denominator is not cancelled, it will create a vertical asymptote instead. Now, to determine the vertical asymptote or the holes in the graph of a function, we have to find the value of x that can give the denominator a value of 0. So, to find vertical asymptotes or holes, we're going to follow these two very simple steps. First, we're going to factor both numerator and denominator. And the reason why is because we want to see if there is a possibility of canceling a common factor. And if there are common factors, there will be a hole on the graph. Now, once you have numerator and denominator in factored form, then you continue with the restrictions. And the restrictions are found by making the denominator equal to 0 and solving for x. Now, x different than whatever the restricted value is will help us determine the vertical asymptote, which we write it in the form x equals whatever the restriction value is. The restricted value is, whatever the restriction is. Okay, now, if the function happens to have a hole at this restriction, then you will have to evaluate y at the restriction. Let's take a look at some examples together. So we are given a bunch of equations here, and we're going to have to determine the vertical asymptotes and identify if there is any holes and determine them. So we're going to start with example 1, 3x minus 1 over x plus 2. Check to see if you can factor. Nothing factorable in here, so we're going to jump to restrictions. Now remember that the restrictions are always hiding in the denominator. So we're going to say x plus 2 cannot equal 0, which means x cannot equal negative 2. So therefore, we're going to say that this function will have a vertical asymptote right at x equals negative 2. That's it, that's all. Now, we're not asked to determine the behavior or anything like we did in the previous example. That was done just for the purpose of understanding, how they work, like what they do to the graph of a function. Now, In the next example here, we have 2x minus 3 over x minus 6. Why do I have the impression we just did this? That was our example. So we're going to have x minus 3 in here. As you can see, the restriction in this case will be x minus 3 different than 0 or x different than 3. And we're also going to say that the restriction is simplified or removed because of the common factor of numerator and denominator. Therefore, at x equals 3, the function will have a whole. Now, if you find that the function has a whole, you have to find the coordinates of the whole. And for this, we are going to use a simplified form of the function, and that is very important. So what does that mean? Now that we have determined what the restrictions are, then we're going to rewrite the function f of x in its most simplified form as f of x equals 2, comma, and then we're going to list the restriction x different than 3. Now, if the function as a whole, we're going to find the restrictions by using the simplified function. Why is that? If you substituted x equals 3 in the given function, then the denominator will become 0. So it will be undefined. The function is undefined at that point. So I'm going to say here, use the simplified function. Well, in our case, as you can see, f of x equals 2. It doesn't really depend on x, which means that the y value will be 2 at any x value, including x equals 3. So therefore, we're going to say that the whole is going to be at x equals 3 and y equals 2. Now let's take a look at our next example. We have x squared plus 1 over x squared minus 9. We'll try to factor first. Numerator is not factorable. It looks like it is, but it's not. X plus 3, x minus 3 is in the denominator. And we don't have any common factors. We're going to jump to restrictions. And restrictions are found by making every factor different than 0. X minus 3 different than 0. So x different than 3. So we have two restrictions. They're not simplifiable. So we're going to say the vertical asymptotes are at x equals negative 3 and at x equals positive 3. So two vertical asymptotes. Let's move on to the next example. Every example is slightly different. So gx equals x squared minus 4 over x squared minus x minus 2. So I will try to factor first. X plus 2, x minus 2. And denominator in factored form, x plus 1, x minus 2. Now, the restrictions in our case will be x plus 1 different than 0 and x minus 2 different than 0, or x different than negative 1 or different than positive 2. Now, notice that the second restriction is simplifiable. So we'll say that g of x in simplified form would be x plus 2 over x plus 1, providing that x is different than negative 1 and different than 2. You see, once you simplify, you no longer see the restriction. Now, we're going to say that here, the function will have a vertical asymptote because it's still in the denominator, whereas right here, the function will have a whole because it's a removed restriction. Or removed asymptote, we should say. Now, what are the coordinates at the whole? Then we're going to have to find the coordinates of the whole by using the simplified function. So g of 2 would be equal to 2 plus 2 over 2 plus 1. And that will give 4 divided by 3. So therefore, the coordinates of the whole would be x equals 2 and y equals 4 over 3. One more example. So we have px equals x squared minus 4x plus 5 over x squared minus 5x plus 6. Let's factor first. It makes it easier for us to identify the vertical asymptotes, but we also want to factor the numerator to check for holes in the meantime. So we have x minus 5, x plus 1. Sorry, where are we? X squared minus 4x minus plus 5. Okay, so that is not factorable. And then denominator is x squared minus 5x plus 6. So that's x minus 3x minus 2. Now, as you can see, we don't have any common factors. So the restrictions will be x minus 3 different than 0, x minus 2 different than 0, which tells us that x is different than 3 and different than 2. And that tells us again that vertical asymptotes are at x equals 3 and x equals 2. So 2 vertical asymptotes. And in the last example, I asked that you draw or you create your own example of rational function. It contains one whole and 2 vertical asymptotes. And you will probably see this as part of a communication or thinking questions in your evaluations. And it's a fun and easy exercise, obviously. So if I want the graph of a function to have a whole, that means that I need a factor of the numerator to simplify a factor in the denominator. So here we go. I made this by giving both numerator and denominator the same factor. Now, for vertical asymptotes, we still need to have the 2 vertical asymptotes so that we can have 2 vertical asymptotes. And then for this, in this case, I'm going to choose x plus 5 and x minus 7. Now, it is up to you if you want to add something else to the numerator. It doesn't really matter. It won't affect the vertical asymptotes. You can add a constant number here. You can add a polynomial function of whichever degree you prefer. It doesn't really matter. So this function will have a whole at x equals 2 and vertical asymptotes at negative 5 and 7. If you were to find the coordinates of the whole, then you will have to determine the value of the function at 2, but with a simplified restriction. So that would be equal to 1 over 2 plus 5 and then 2 minus 7. So 1 over 7 times negative 5, which is 1 over negative 35. So therefore, the whole will have the coordinates of 2 and negative 1 over 35. So that was it about the vertical asymptotes. In the next video, I will go over the horizontal. I will go over the horizontal asymptotes together. And as always, really appreciate you learning with me, and bye for now.